Hello, hello. Hello.
Check. Is it audible there? Am I audible in the hall too? Just huh? Okay. Thanks.
Mic testing 1 2 3. Am I audible? Yes, I am. Thank you so much.
hello.
May I have your attention, please? If any of the faculties or schools have the vehicle number of 3404 RJ14, your lights are on, so the battery might die out. Check, check. Uh, Mic testing, 1 2 3. Perfect, sir. बिट्स की वेबसाइट पे दूसरे चंद्रशेखर सर का था तो है नहीं, यहाँ पे लिख लेता हूँ. We shall start the program in 2 minutes. Thank you for your patience. A very good morning to everyone present here. Honorable Chief Guest of the Scientific Model Competition, Professor Chandrasekhar, Senior Professor Emeritus, BITS Pilani. Our guest of honor, Dr. Gaurav Purohit, Senior Scientist, CSIR Siri Pilani. Dr. S.M. Prasanna Kumar, Director, BKBI ET. Shri K.K. Parik Sir, GM Commercial, BKBI ET. Dr. Anil Kumar Sharma, Principal, BKBI ET. Mr. Manoj Kumar Gaud, Principal, BTTI Diploma Section. Our esteemed judges of the competition, Dr. Y.K. Gupta, Head of Department, Applied Sciences and Humanities, Dr. Nimish Kumar, Head of Department, Computer Science and Engineering, Artificial Intelligence, Data Science and Information Technology, Dr. D.C. Sharma, Head of Department, Mechanical Engineering, Dr. Smita Parekh, Head of Department, Electrical Engineering, Dr. Vikas Punia, Assistant Professor, Department of Electronics and Communication Engineering, Mr. Manoj Kataria, Assistant Professor, Department of Computer Science Engineering. Coordinator of the Scientific Model Competition, Dr. Santosh Jangir, Head of Department, Electronics and Communication Engineering and VLSI. I welcome you all to the Scientific Model Competition at BK Birla Institute of Engineering and Technology, Pilani, a showcase of innovative projects by the diploma and school students in the region, a celebration of the next generation's talent and dedication to science and technology. Let us start by welcoming our guests. For the same, I request our student coordinators to present a bouquet of flowers to the Honorable Chief Guest of the Scientific Model Competition, Professor Chandrasekhar. Dr. S. M. Prasanna Kumar, Shri K. K. Parekh Sir, Dr. Anil Kumar Sharma, Mr. Manoj Gaur. I thank our student coordinators for the same. To inaugurate this event and symbolize the pursuit of knowledge, let us now proceed with the traditional lamp lighting ceremony. I request our dignitaries to please light up the ceremonial lamp. Thank you, esteemed dignitaries. The scientific model competition, organized by the B.K. Birla Institute of Engineering and Technology, Pilani, is a platform that celebrates the spirit of scientific innovation among diploma level and school students in and around Pilani. This event serves as a showcase for the ingenious creations and projects developed by young minds, highlighting their talent and dedication to the field of science and technology. The competition provides a unique opportunity for participants to present their scientific models, offering a glimpse into the cutting edge ideas and solutions emerging from the next generation of innovators. With a distinguished panel of judges and esteemed guests, the event aims to recognize and reward outstanding contributions, fostering a culture of curiosity, exploration, and creativity in the scientific community. The scientific model competition is not just a contest, it's a platform that nurtures passion for discovery and encourages the pursuit of knowledge in diverse scientific disciplines. I take this opportunity to request Director Sir to kindly address this August gathering. Please, sir.
Well, good morning to one and all. Respected chief guest of today's gathering, Professor Chandrasekhar. Guest of honor, Professor Gaurav Purohit from Siri. Parik sir, principals from different colleges, head of the departments, and coordinators from different schools, young students from schools who are very enthusiastic in displaying their models which they have prepared in their school. Extending warm welcome to one and all. This platform we thought of creating to the young minds so that they put forth their talent, their innovative ideas that they have learnt in their classrooms, so that that can be shared among the different students of different schools and their thoughts, their ideas, so that the science level in their studies, in their career further, to evolve themselves, to know the different areas, different fields of innovative works going on in the scientific model preparations. Once we talk about this scientific models, there are varieties of domains of the models available with us in general to talk about even our uh, the nature concerned, like rain cycle, our Bohr atomic system. So these are all some scientific models which are in general studying through your curriculum and all that. But at the same time, when the question comes in about the implementation of them, when we thought of about making such models out of it, with ideas provoked in your mind, debated and discussed with your friends about why this technology cannot be used for the public use, society and all that. At that level, when the thought came into your mind, you must have discussed with your teachers, saying that this model we want to prepare and know the ideas more and more and keep on improving stages wise. And then when such platforms are made, so you can come and display of your own and keep explaining, saying that this is how the model works. Now in this process we thought that the mind evolution in terms of science and technology, which are prevailing so high now compared to the any other earlier centuries, so these changes or the modernization occurring in terms of the science and technology is worth everyone to go through. And at the same time, when we share each other about your innovation, about your model, and keep explaining, young brains, surely you will be learning more here than you are displaying your own single model. So with that intention, the organizers thought like we shall invite especially school kids with their thoughts and ideas and models prepared by them and display here. And at the same time, when we invited many schools through mails and personal requisitions and all that. So far, 11 schools are participating here. And out of these 11 schools from Junjunu, from Dundlod and Pilani and nearby areas, 51 projects have come up from those 11 schools. And even our own college campus, ITI and Diploma, we got 20 such projects. So total, we are displaying 71 projects here. So you can just imagine what would be the varieties of the fields that are involved in this. Once you go through, you will come to know that the displays made there are all having so much involvement of the students' interest. And again, as I said, like when you talk each other, model to model, and their ideas, you will enhance yourself the quality, and of course, your next higher level of education will become so interesting and create some uh, uh, energy in you, so that you will concentrate more towards such emerging areas, modern areas, and all that. So just to point out what all the new areas, new emerging areas that have come up from compared to the earlier technology and all that. Nowadays, anything you take, even the Chandrayaan you can take, what should be the level of work that must have been done to make a object to go there and uh, land on the moon like this. So communication, TV technology, mobile technology, varieties of fields are there. Huge number of uh, fields are there one has to come across. So this is uh, really a good platform for you, good ecosystem for you, so that you will learn and more. So our objective of this program, scientific model competition, was to make you to go through and understand the different logics and implement in due course and make your further higher studies very interesting and learn more and more, lot and lot. Thank you.
Thank you, sir, for your warm words. The eagerly anticipated scientific model competition at BK Birla Institute of Engineering and Technology in Pilani is set to bring together a dynamic cohort of 179 students from over 12 diverse institutions. This gathering not only showcases the rich tapestry of academic backgrounds but also signifies a collective dedication to scientific exploration and technological innovation. With a remarkable offering of over 71 projects, students from these institutions will present their ingenious solutions across an array of disciplines such as physics, biology, electronics, computer science, agriculture, and more. The sheer volume of projects underscores the depth and breadth of intellectual curiosity present among the participating students. The competition serves as a melting pot of ideas, fostering interdisciplinary discussions and collaborations. It represents an exciting opportunity for students to share their innovation and engage with peers from different educational backgrounds and contribute to the growing scientific culture within the academic community. We have participation from the Sire Vidya Mandir, the Dunlod Public School, the Bal Niketan Senior Secondary School Pilani, the Birla School Pilani, the SS Vodim Vidya Mandir Junjunu, the BPS, that is the Birla Public School, the Birla Balika Vidyapeeth Pilani, the Birla Shishu Vihar Pilani, the Birla Technical Training Institute ITI section, the Birla Technical Training Institute Diploma section, the Tagore Public Senior Secondary School Pilani, the Rakesh Senior Secondary School Pilani, and Sri Jamuna Mishra Academy. It is now an honor for me to read a brief introduction of our chief guest, Dr. Chandrasekhar. Professor Chandrasekhar, currently serving as a Senior Professor Emeritus at BITS Pilani, has a distinguished academic and professional background. Previously, he held the position of Director at CSIR, Central Electronics Research Institute, CSCD in Pilani, Rajasthan, India, from 2003. His extensive research spans VLSI design, analog IC design, mixed signal design, processors, applications specific processors, CAD for VLSI, physics, and modeling of MOS devices, as well as VLSI system applications. Dr. Shekhar earned his MSc degree in physics in 1971 and completed his PhD in 1975, both from BITS Pilani, India. He is recognized as a fellow of the IETE and holds life membership in esteemed organizations such as the Indian Physics Association, Semiconductor Society of India, and the Indo-French Technical Association. We are extremely fortunate, sir, to be here in your presence. May I now request you, sir, to kindly address this august gathering. Please, sir.
Good morning, everybody. Honorable Director Sahab, Principal Sahab, distinguished invitees, HODs, members of the faculty, uh, school faculty if they are accompanying the students, and my dear students. It is indeed a privilege for me to be here facing you all and seeing some very bright faces who have come to display the best of their sort of application ideas, application of ideas, and are jostling with each other, both competing and making friends and learning from each other. I think such events are a great occasion for young people, both to learn as well as to teach, which means essentially share. And each one in the process improves himself. I always say that competition should always be taken in a positive spirit because your competitor is your best friend. Even though you might be feeling a little jealous at times, somebody will win prize and maybe you will not. But believe me, your competitor is your best friend. And why do I say so? So imagine that you are an athlete, right? And you want to run alone. And you run alone, it feels so boring. You run with a friend, he tries to outpace you, you try to outpace him. Both of you enjoy your running and both of you improve. That's what competition is, and that's the spirit in which competition should be taken. Competition should not be taken in the sense where competition breeds jealousy or hiding of secrets or stuff of that nature. Now, let me say a few words to my young friends. We hear the word science, we hear the word technology, we hear the word engineering, we hear the word innovation, and of course, we also hear the word startups and you know those kind of things. So let me delve a little deeper in terms of definition and understanding of these words. You always see that science is curiosity driven. We are curious about natural phenomena that are occurring around us, and we want to understand these phenomena. So that curiosity is God given to us. It is natural. We can't help it. So that is the root of science. So really science is curiosity driven. Now, whatever we are curious about, we would, hypothesize. We will try to say maybe it is happening because of this. Maybe this is how it happens. There is always a maybe. That's the hypothesis part. The scientific method is where we hypothesize, we make a guess, we then try to test that guess by performing an experiment and try to test it out on a larger scale by making many more experiments. And if our guess or our hypothesis still explains all those experimental observations, then we say probably we have a theory. We have something that works, right? if what we had guessed explains some experiments but not others, you find anomalies, then you revise your hypothesis, you revise your guess, you make another guess, such that this guess can cover the earlier experiments and those experiments also where the previous hypothesis or guess failed. And now you have a stronger hypothesis. And a hypothesis that survives all challenges, a hypothesis that survives all challenges becomes a theory in science. So this is the scientific method. Scientific method is very solid because we are not afraid of failures. We say, I guess this is how it happens. So I float that idea. People try to test that out. Somebody says, no, your idea fails. Here I have a better idea that works. Somebody else challenges it and says, look, this also fails. So I have an even better idea. And a hypothesis or idea that survives all challenges is a theory. Now, that's the way scientific theories have been discovered. We call in science what we find out new is called a discovery. Why do we call it a discovery? Because we didn't create it. It existed. We only uncovered it. That principle was always governing. Only thing we did not know. It was covered from us, so we discover it. That's called a discovery. So scientific theories are of great value. Why? Because once you know a scientific principle and you have tested it, it has become a scientific theory, then it is very widely applicable. So you can actually predict the result of an experiment that you have not yet conducted. If your theory is sound, it is really a theory, it is robust, then you can set up a hypothetical experiment. One way is you actually go and do that experiment. The other thing is you apply theory to that situation and come out with a result. And if the theory is good, then your result would be good. You perform the experiment, you will find the same thing. Which means scientific theories give you the power of prediction. That's a very, very important thing. I can predict something. Okay, given a situation, I can apply theoretical, proven theoretical ideas, and I can say, look, this is what you will see if you do this. And lo and behold, that's what you indeed see. So that's the power of prediction. That's why scientific theories are so important, right? Engineering, on the other hand, different from science, it is need driven. Science is curiosity driven. Engineering is need driven. You feel the need of something. You feel there's some pain, some difficulty. Maybe I should find some way to help. And you create some kind of a device, contraption, some kind of a machine, some kind of a arrangement, kuch jugaad, jod tod. That's engineering. So engineering is a human creative effort, and the result of engineering is an invention. Because what you make may not have existed earlier. It is something new. It did not exist in nature. Nature did not give you that. So if you look around our life, you would find that a lot of it is really a result of inventions. The materials you see here, the display you see here, nature never created it, right? So there is no discovery there, but it is an invention. We created. So new materials have been created, new machines have been created, new devices have been created, new means of communication have been created, new tools have been created. All of that is engineering. So engineering is really need driven. Necessity, as they say, is the mother of invention. So you feel the necessity, you feel need, you do something, you put together, you create, you invent. That's invention. Now, if you look at the history of science and engineering, initially they were quite apart. They had no relation. They were like two parallel rails of a railway track. There were people who were purely curious. They were pursuing philosophy and science. There were others who were trying to, do engineering and come up with some solution. They weren't interacting. The interaction really came in the industrial revolution era. The first industrial revolution, as you know, it took place, started, at least originated in what is United Kingdom today. That's where people said that if I want to engineer something, I try out, but what is it that I should try out? How do I know it will work? How strong it will be? That's where the scientific understanding started helping. Science had begun to characterize materials, science had started establishing theories. So to your engineering proposed engineering solution or your imagined engineering solution, you can apply scientific theories and you could test it out. You could see how it will perform, how strong it will be, etc., etc. You know, only the other day we read in the newspaper that a very promising uh, young entrepreneur heading a very successful software company, the founder and the chairman of that company, you know, the founder passed away unfortunately, and the chairman was very seriously injured because, you know, there was a function to celebrate 25 years. I'm sure some of you would have read that news. A 25-year celebration, and there was kind of yeah, a chain broke. Now it is, it shows poor engineering. Why poor engineering? Because I most probably can imagine that they never studied the quality of the material they used, its mechanical properties, how much stress it will take, how much strain will break it, etc., etc. Those kind of accidents should not happen today, but it happened. So engineering started benefiting from science. We all have heard the story of James Watt. James Watt basically was an engineer, right? He saw that when water boils, the lid is blown off, it starts jumping up and down. And he saw that there is a force, surely there is a force. How can I make good use of this force? And that's where he saw that if a force is once applied from, let's say, my right, it will push the piston or dhakkan one way, and if it is applied from the other side, it will push it back, and so you can create a back and forth motion that can be converted into a rotary motion. And so steam engine was born, right? So that was an invention. The Boyle's law and Charles' law were already known, but it is one thing to know Boyle's law and Charles' law, and it is quite another thing to invent a steam engine. So that's what engineering is. But engineering today, very complex engineering systems have been built, right? So if you look at you know uh, Chandrayans, or if you look at the Apollo mission kind of thing, or even if you look at your cell phone, it is a marvel of engineering, right? Your cell phone has chips, all of you know, they typically contain more than 1 billion transistors. So how can you build a system of so many things? How can you imagine? Now, if you, so that is where computation and mathematics comes in. You know, science would not have been possible without arithmetic, mathematics, or counting. Counting is fundamental because counting gives us quantitative idea. Otherwise, our ideas would be qualitative. So today we can say so many degrees Celsius is the temperature, and we can go down to 0.000 whatever, depending on resolution, fraction of a Celsius. But if we didn't know how to count, all we could say आज ज़्यादा ठंड है, कल कम थी, right? That's about all. We could talk only qualitatively. There would be nothing quantitative, and therefore there would be no predictability. Predictability requires precision. You should be able to say this is what will happen, which means unless there is numbers counting, you would not do that, right? So that's what mathematics brings. So no wonder that most scientific theories are expressed in mathematical terms. They are not expressed in qualitative terms, right? So that's very, very important. However, if you express theories in quantitative terms, and if you have a complex enough machine, to apply the theory to that complex machine to solve becomes very difficult. So it is one thing, you must be studying all those questions. If a ball is thrown with this velocity upwards, how high it will go, or at a particular time, what its velocity will be. But if there are a million balls striking each other, going all around, what will happen? Surely you know the basis of how to solve it because your theory works. You still are in the domain of Newton's laws. So if they are colliding, action reaction are equal and opposite, forces are working. But there are a million balls, so how do you solve this problem? Which ball is when at what time? That's where computation helps. That is where computing machines. So computing machines were the more recent machines. Earlier machines were meant to lift weights, right? So whether they were levers or they were pulleys or whatever, uh, levers and pulleys, we still used our muscle power, but they were force multipliers. So you would require less force, but for longer time to pull something which is much heavier than you could directly pull, right? Then came the steam engine, then came the internal combustion engine, then came electricity, then came the electrical engine. So they all replaced our muscle power. But then our brain power required some assistance too. And that is where I gave you this example. If there are a billion atoms striking each other in a container, where is each atom at what time? What are they doing? Can you tell that? So you have theoretical ideas, but to find a solution, you require a computing aid. And that's where our computers have come in, right? So gradually all these things have been moving, and our ability to do better engineering has improved as a result of, we still need to propose a creative engineering solution, an idea how we would like to put things together. But we can draw on the scientific knowledge, we can draw on computational tools to then predict that what we are imagining, how it will work. And lo and behold, today, this is what has led to computer simulations, and we can practically simulate everything. Many things. And simulations, because our theories and our computational models are so accurate that your predicted results are exactly or very close to your actual results. So you can do virtual prototyping. You don't need to make a thing. You can make a virtual prototype, a computed model, and then test out different varieties and figure out what is that works best, and you can go ahead and do that. So that's engineering. So the marriage of science and technology was a very powerful marriage. I would say it is, you know, what should one call? I mean, to me, in the world of marriages, this is the most important marriage, right, that ever took place, because its progeny is so powerful. It is so absolutely powerful. And then, of course, computation also get into the game, and we have the capability that we have today. Okay, but human aspiration is never satisfied. Now, complex system. We know all the theories that should explain the weather conditions on every cubic inch of the earth. All the theories are known, right? The point is, can we compute? And the answer is, we still can't compute that much. We can compute a lot than what we could compute earlier, right? We can model a compute car. We can make a computer model of a car. We can make a computer model of a crash. We can make a computer model of a nuclear bomb blowing up. We can do all of that. But this is such a big system that we cannot, we know all the theoretical ideas that if you tell me I can write an equation, even a dull guy like me can write an equation, who is not an environmental scientist can write an equation, but you can't solve it. That's where this race to build ever faster computers is there, and that is where people think that we should go to quantum computers. That's the new area where we are going. Traditional computers are going into what is called exascale computing, right? So we already are at petaflop level where you do 10 raised to the power 15 computations per second, but we now want 10 to the power 18. But even that is not enough. So you want more. That's why our weather predictions don't go as well, right? We see weather predictions, but the reality turns out to be somewhat different. So, but it is a lot better than what it used to be. That's also for sure. So those, all that's a march that goes on. So that is, then let me now say a word about innovation. We hear this word very often today. So between invention and innovation, invention is something which is really epoch making, like invention of steam engine, invention of internal combustion engine, invention of motors, electrical motors, right? They are epoch making. As opposed to that, innovation is that you feel a pain point and you come up with an idea that tries to solve that pain point. And pain points are always there. It's only that many times we don't care to look at them. We look at them and pass by. When you look at something, you don't always see it. So, to students, I would say, please take note that seeing is not observing. Looking at things is not observing. You can look at a thing and may not see, which means you may not get the underlying import, underlying important situation. You may miss out on that. So your brain may not have processed what you saw. It may not have correlated it with the rest of the life around. So you you look but you don't see. Now, if you have to become an innovator, you ought to learn to see so that you can see. If you look around life with empathy, you find enough pain points. And you then look at choose a pain point that you might like to address, you would like to address, something that touches your heart. And you might say, this is a pain point I would like to address. And then you start putting together a solution. So put together a solution, analyze it, because of scientific theories help you analyze it, try to build a prototype, test it out, go to the next better kind of improved idea that you may have hit upon while doing all this until you come up with a solution. And that solution is something that is science, engineering, technology in action for the good of this society. Technology, when we use the word technology and engineering, we use very often, Institute of Engineering and Technology. But technology is, so there is a popular saying that science is knowing the rules of the game. Rules of the game were set by the creator, right? The way nature works. But we try to gain an understanding of those rules, that is science. So science is understanding the rules. This is a game where rules were not told to you, you were thrown in the game. So jao khelo, right? You have to find out what are the rules of the game yourself. Engineering is like playing the game. It's not just knowing the rules, but it's playing with the rules, kicking the ball around, giving a pass to somebody. And technology is learning how to score the goal. So technology is really engineering perfected. When you can really shoot a goal, you have technology. Otherwise, you are doing engineering. That's fine, but you don't have a technology. Technology is when you can score a goal. Your solution is robust, repetitive, economic. It works. It works every time. Innovators develop new technologies in that sense, new solutions. And as I said, it starts with the observing pain point, uh, by looking at things and seeing them and being empathetic, picking up something, and then applying all that you have learned. So, that what you have learned is there here in your minds. It is because of empathy and desire to create something that you draw upon it. You mix it up in a creative fashion and you come up with a solution, and then you test that solution out, you improve on that solution, you do something more. That's how you basically go on improving until you get something which really can be, let out. So that part is what our country is in that phase. It took us in the many years. India had great scientists before independence. So science was there in India. Engineering came later. Technology is relatively new still. So Chandrayaan is a full-fledged technology for sure, right? But we are now making our own aircraft, but we are still not making aircraft engines. That's a technology we have been struggling for 40 years. These things are not tiny, right? They take time, but that's where you need to go, right? Technology for building chips, technology for building computers, technology for image processing, all new technologies keep coming. We have to be, that's what creates value for society. That is what brings what one calls richness to our lives. And richness is not, I mean, you can then translate it in money, but it is really living a rich life, right? So I hope that you would all learn to apply what you have learned to solve problems. And what I see, I see very hopeful signs that I see as I pass by a school, I see a board that this school has Atal um, Innovation Lab, right? So you are making and breaking, that sort of thing is relatively new, but it is very good. One thing that I appreciate about particularly Americans is that they have, each house has a garage, and the garage is kabad khana. So you have lots of things packed in the garage, and that is the place where young people like you go sit and try to do jod tod, because you're not allowed to mess up the household. घर को मत तो mess up करो, garage में बैठो, वहाँ अपना सामान रखो, keep whatever you, वो तो कबाड़ खाना है, जो भी आपको लाना है लेके आओ. Parents encourage you to buy those things and you try out. And it is not a surprise that we hear success stories from garage to billion-dollar companies, right? So that effort of trying to build things is something that we have to accept and, you know, take into our culture. If you don't build things, you would be a philosopher. If you do not build things, you will end up being a philosopher, which is wonderful, sure, but it has limitations. And if you begin to build things, so that culture of, you know, having easy access to components, tools, building, we aren't all that good at it. So we are either doing academic line or doing the other line, which is considered not academic but more practical. I think we need to mix these two. And that garage culture, I would urge, wherever you have the opportunity, whether it is in your school, it is in your home, um, even if you have to quarrel with your parents or whatever, please by all means learn to put things together as well. Otherwise, you understand, you keep imagining, but you don't build. And if you don't build, you don't improve. So that's something which I will urge to you. I hope that most of your models would be display of the spirit. So you might find what all I said was redundant. That would be really, I would be the happiest person if it is totally redundant, because you are already practicing it. So it would be my best wishes to all of you going forward. Uh, May tomorrow's India, because look, people like me are now old. We look forward to our young people to take the country forward. We did put in our effort, and we did put in strenuous effort. We still continue to put in effort, but surely it is the younger people who are the front horses of any chariot, and you are really those people. So all that I had a quick share to do with you, I thought I have done. I thank you for your patient listening, and I thank the college, Principal Sahab, Director Sahab for inviting me, giving me this opportunity. Once again, best wishes to all of you. Thank you very much.
Thank you so much, sir, for your extremely insightful address, for sharing your wisdom with the young minds and highlighting the nuances of science, technology, and engineering, detailing the characteristics of innovation and invention. May I now request Director Sir and GM Commercial Sir to kindly felicitate our chief guest. Please, sir. Thank you so much, sirs. We have in our presence our guest of honor, Dr. Gaurav Purohit. I request our student coordinators to kindly welcome him with a bouquet of flowers. I am extremely fortunate to read a brief introduction of our guest of honor, Dr. Gaurav Purohit. Dr. Gaurav Purohit is a senior scientist at CSIR Repilani, where he has been actively contributing since 2016. Concurrently, he holds the position of assistant professor in engineering sciences at the prestigious Academy of Scientific and Innovative Research, ACSIR. Dr. Purohit earned his PhD in 2019 from BITS Pilani, specializing in the intricate domain of energy efficient digital baseband architecture for software defined radios, with a particular focus on 6/5G and B5G wireless standards. His academic journey also includes a master's in communication systems from BITS Pilani and a bachelor's in electronics and communication engineering from the University of Rajasthan. Beyond academic accomplishments, Dr. Purohit has been a key figure in various research endeavors. Notably, he led the CSIR funded project on intelligent data analytics algorithms for predicting air quality monitoring. His international exposure includes a stint as a visiting project researcher at Hiroshima University, Japan, and an active participation in the Japan Asia Youth Exchange Program. His research interests span energy efficient reconfigurable designs and the applications of AI/ML algorithms in diverse fields such as air quality monitoring, telehealth, and drone tracking applications. With numerous publications in reputable journals and conferences, Dr. Gaurav Purohit exemplifies a dedicated contributor to scientific advancements, bridging the realms of academia and practical research. It is an honor for us, sir, to be here in your presence. May I now request Principal, sir, to kindly felicitate our guest of honor. Please, sir. Thank you so much, sirs. With this, we have completed the first leg of today's activities. I invite our guests and mentors to join us for a high tea, after which we shall commence the evaluation and demonstration of projects. Please proceed for the high tea, guests. I request you. I request the students to kindly remain seated for a while.